Okay, now I'm gonna start to talk about um, the look at an example. If we have a RC circuit with the AC source, how we can solve it. Up to this point, all the example we did was the transient condition. If we had the DC source. Now I want to see what would we do if we have the AC uh, source in the circuit. So let's assume we have a circuit like that. So we have the battery, and then right here, so we have the battery um, that has a sinusoidal format. So it's going to be 2 sine 200t. So, and it's connected to, and there's going to be a key, and then we connected through the resistance. It's going to be 5 kilo ohm. There's going to 5 kilo ohm. So this is the resistance that we have. So this is the R, and then we have the capacitor um, as this. So this is the C, and it is a 1 microfarad, and we know the voltage at this one is going to be VC over T, uh, and then goes back to the source. Um, so this is what we have, and assume at the T is equal to 0, we will close the key. So if at is open at beginning of 10, and at the T equal to 0, want to close the T. But before we close the key, we also know that at the very beginning, the capacitor is not empty, is not fully discharged. So we know at the very beginning, also the at the V at T is equal to 0. It has one, the VC, the voltage at the capacitor is 1 volt. So it already has 1 volt of M. So it's partially or somehow charged at the beginning before we close the key. And then when we close the key and we connect it to the source, we want to see uh, how the current goes through that capacitor is gonna start to change. So at t is equal to 0, we'll close the key. So example, at t is equal to 0, we close the key, and then see what we have here. So first of all, when we have the circuit, so we'll have to write the very first step is that we have to find the differential equation that describes the condition in our circuit. So assuming our circuit, we will have the current go through, and it's a single loop, go through that. So I can go ahead and write the KVL, sorry, KVC, uh, 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 KVL for this one, and to see what happens. So if I write the KVL um, at this loop, what I have, so if I go around and start to write the voltage and assume this is going to be the Vs, I will call it the Vs is equal. So I know that negative Vs plus the V at the resistance plus the V at the C is going to be equal to 0. Um, so assume that's going to be positive and it's going to be negative. So it's going to be equal to 0. See, so if I rewrite that and substitute everything with whatever it's going to be, so I can go ahead and instead of the VR, I'm going to replace the, so let's write it. So it's going to be the VR plus VC is equal to Vs, and then I'm going to substitute each term with with the equation that contain the I. So here the VR, we know that I can use the Ohm law, so I can go ahead and say the IT times R is going to be so if I it's going to be the so V is equal to IR for the VR. Then for the voltage at capacitor, we know that's going to the voltage capacitor is going to come from this equation. So from the 0 to T IT dt plus the VC at T is equal to 0. And then this one is going to be equal to the Vs we have, and Vs here is 200 sine. It's going to be 200 sine 200 t. So this is the equation we have. And as you can see here, what we have here, we want a differential format of equation. We don't want to have the integration into our equation. So to get it into pure differential equation, we just take a differentiate of this equation respect to t. So we get rid of that integration. So if I go ahead and do that, so if I take a differentiate of this equation, what I'm going to have is that so the R is constant going on, so it's going to have d it, that's the function of t over dt. Then for this one, because it's a dt, so it's going to become 1 c I t, and then this part is becomes 0, the v because it's constant, so if I differentiate that becomes 0, is going to be equal to, and for this one it would become 400 cosine 200 t. So this is going to be the equation. And now if I go ahead and times the entire equation with the c to get rid of that, what I'm going to get is that, so I'm going to have the RC dit over dt plus it, and then that's 0, I'm not going to write it anymore, is equal to, is going to be that 400 times c, 400 times c times cosine 200 t. So now we have the pure differential equation in this condition here. So now that we have that, we know that after we find that, there are two parts that we have to find, because it's the AC source we have to find, and the particular solution and the complementary solution. So the first part of doing that is to find the complementary solution. So for the so the particular solution. So we know that the particular solution, and usually the particular solution are gonna be given to us, and it depends on these equation. So it depends on the format of the source. So we know the particular for this case, for the particular solution, for this type of source, for this sine source, is gonna be A cosine 200 t plus B sine um, um, well, so okay, let me just put also that part at the beginning. So the particular solution of what we have is going to be the IP t is going to be A cosine 200 t plus B sine 200 t. So as I said, this particular solution is given to us. So this is the very first step that we have to define this particular solution. And if you look at this, we have the A and B are unknown. So we have somehow find the A and B. How we do that is that we know that the particular solution is supposed to satisfy uh, the the general solution, the main equation that we have here. So if I call this equation, if I go ahead and say this is the equation 1, and then I'm saying that that's the equation 2. So basically we will put 2, we substitute 2 into 1, and that should be satisfied this equation. And by doing that, we will find the A and B. So what we will do to find that, so we'll go ahead and we put the IP into this equation, substitute it there, and then we try to solve it from there. So if I go to the next slide, so if I put IP t in equation 1, that's what I'm gonna say. So we know that the equation 1 was the R, so it was the R C D I rewrite the equation 1 again here dt plus IT is equal to 400 C cosine, so put the 400 C cosine 200 T, and then if I go ahead and put in so it's going to be RC D over DT, and the IP is going to be so if I put there, so this one is going to be IP and it's going to be IP. It's going to be IP, and let me write that also as IP. So it's going to be IPT. So we substitute the IPT in that equation. Now I might replace the IP with its value, so it's going to be the A cosine 200 T plus sine plus B times sine 200 T, then plus again the IP here. So it's going to be again the A cosine 200 T plus B sine 200 T, and this is going to be equal to 400 times C times cosine 200 T. So we have this equation here. So if I go ahead and do the differentiate here and do the calculation, what I'm going to get at here, I'm going to be the RC, then it's going to times negative 200a sine 200t plus 200b cosine 200t, and then we have this term itself, so it's going to be a cosine 200t plus b sine 200t is going to be equal to 400 times c times cosine 200t. So now we have this equation, and we need to go ahead and start to simplify this equation. So if I go ahead and simplify that equation, what I'm gonna get is that if we know that, so let me put this here. So we know that the R, go back. So the R is 5, the value of the RC, and also, so the R is going to be 5 times 10 to the 3, and the C is 1 times to 10 to the negative 6. So if we go ahead and substitute the RC into that, eventually we know that the 200 RC would become 1. So you do the calculation, you will see that. So we have this 200 is going to be times what RC that we have here. The 2 times 5 is going to be 10, and you have 10 to the 3 here, 1 0 from the 10, and 2 0 here, so it's going to be cancelled out by 10 to the negative 6. So eventually this is going to be 1. So if you substitute that in this equation, and in this equation, and simplify that, what we're going to get is that it's going to be negative R A plus B sine 200t plus A plus B cosine 200t is would become equal to 400 times C times cosine 200t. So if I, as I said, if I put the 200 RC in this equation, or put the RC in this equation, and then simplify it, rearrange it, this is what I'm going to eventually get. So when I would get this equation is that if you look at this equation, I have the sine term on the left side. I don't have any sine term on the right side. So this sine term should be 0 in order that we have the equivalence between these two. So to make the, so it's going to give me, so the sine term should become 0. To make the sine term 0, so it means that the negative A plus B should become 0. So in order to get the sine term 0, because I have a sine term on the left hand side, I don't have a sine term on the right hand side, so the sine term should be 0. Then I have a cosine term here, and I have a cosine term here, so these two should be also the same in order that I have this equation correct. So therefore the A plus B, so the coefficient of the cosine here should be equal to the coefficient of cosine on the right hand side. So it's going to be equal to 400 times C, and we know the C is going to be basically going to be 400, and the C is 1/10 to the negative 6. So if we solve these two equations at the same time, what we will get is that we will get the A is become equal to 200 times to the 10 to the negative 6, and then we get the B, and then B would be equal to also 200 times to the 10 to the negative 6. So and both of them I have the, so it's going to be in the amp. That's going to be in the amp. So this is a this is the A and this is the B. So I'm just remove the unit in case it's going to get you confused. So this in the amp and both of them in the amp because we are writing it in for the current. So this is the A and B we will have. So therefore I can have the my particular solution. So if I go ahead, I can write my particular solution. The IPT is going to be 200 times 10 to the negative 6 cosine 200 t plus 200 times 10 to the negative 6 sine 200 t. So this is the particular solution that we have. So that's the second. So the first step was to find the pure differential equation. The second step was to find the particular solution. The third step is that we write the general solution. So the general solution is going to be the IPT plus the complementary solution, basically the ICT. So this is what we will have. So we have the IPT, so we have to find the ICT in that case that we want. So that's the general solution. So it's going to be the general solution. This is going to be the particular solution, and this part is going to be complementary solution. When it comes to the complementary solution, is that we know the complementary solution. So we know that the complementary solution has a form of the complementary solution is the solution that satisfy the equation if we remove the source from the general differential equation. So if I go back here, if this equation 1, if we remove the source, then the complementary solution is the one that satisfies that is the solution to that. So basically the complementary solution is the solution to equation 1 without the source. So if I go ahead with that, so the complementary solution is a solution of equation 1 if source is 0. Is 0. In other way is that if I have so if I go ahead and put complementary solution, which is going to be ICT in equation 1, and 0 um, uh, the right hand side. That's what we're going to do. Or instead of saying the source, let's put it as if the right hand side is 0. So the fourth term is 0 if the right hand side of equation 1 is 0. So if I put the IC in equation 1 and 0 the right hand side, what I'm going to get is going to be the RC DICT over DT plus ICT is equal to 0. So that's it. So I make the right hand side 0 and I substitute the IT with the ICT with the complementary equation. If this is that, we always know that for the complementary solution is then this ICT would be K e to the power of negative T over tau. And we can skip these steps. Always the complementary solution is going to be like that. So we can skip all these steps and go ahead and say, okay, we know the complementary solution is always like that. And we don't need to write this step, but it's just to know where it comes from. Otherwise, the complementary solution is always like that. It's always k e to the power of negative t over tau. So now I'm go ahead and substitute the complementary solution in general solution. So if I if I go ahead and say put both ICT, or let's put IPT, the particular solution, and ICT in general solution. So we are here. So stand the steps, and then the next steps that go ahead and put in there. So therefore, that general solution is going to be the I. Is going to become the particular solution is this one. So I know that's going to be 200 times 10 to the negative 6 cosine 200t plus 200 times 10 to the negative 6 sine 200t plus. So this is the particular solution. So this part. So this is the particular solution. So it's the IPT, and then plus the complementary solution, which is going to be the K e to the negative t over tau. And we know that the tau, because we know we are working with the RC system, RC circuit is the RC circuit. We know that tau is going to be RC. If it was if it was the RL system, it was the L over R, as we discussed it before. So this is going to be RC system, and this part is going to be ICT. So if you look at into this equation, the only unknown we have in this equation is the K. If we find the K, because the tau is RC, we know both R and C values. So the only unknown is the K. So we need to find the K. In order to find the K, uh, we will use the initial condition. So we put the initial condition where the t is 0 in this equation, and then we find the k there. So to do that, um, so we uh, um, uh, use initial initial condition where the t is 0 in general solution to find k, or basically put initial condition into, so instead of use, let's say put initial condition. So we have to go and see what is the I at t0. So we want to find the I exactly when the t is 0. So at t is equal to 0, what we are going to have is, this is going to be our circuit. So it's going to be the battery and connected, assumes connected to the R. So it's going to be the R, and it's going to be the C, and it's going to be here. We know at the beginning, when we talk about, we know that at the very beginning, the VC at T0 is 1. It's 1 volt. We know that. And this one is going to be the VR, which we don't know what it is. And the VS, the voltage at the source, is the VS is going to be 200, what was that? So it's going to be 2 times sine 200t. Okay. Now we know that at if I go ahead and write the again the KVL here, it's going to tell me the negative VS plus VR plus VC is going to be 0. Now at t is equal to 0, we know that the VS is equal to VS at t0 would be 2 times sine 200 times 0, which we know the sine of 0 is 0, so it's going to be 0. So at t0, this is going to, the Vs is 0, and also we know that the Vc at t0 is going to be 1. So if I put all these into that equation here, if I use this, it's going to be this one is going to be 0, so it's going to be negative 0 plus the VR, we don't know what it is, and the VC is 1, is equal to 0. Therefore, the VR is going to be negative 1 volt. So this is the VR at T0, or let me put it here. So VR at T0 will become negative 1 from that equation. And that we have, so it's a negative volt. So now that we know the VR at T0, I can go ahead and look at here. If I have the I go through this circuit, or let's put it here, so it's going to be I at T equals 0. So I know the I go through that VR, so I can go ahead and write the Ohm law for this R. So the Ohm law is IR. So I know that the VR at T0 is going to be equal to the I at T equal to 0 which is what we are looking for, times R. And if I substitute the value of those, so the VR at T0 is -1, is equal to I at T0, which is what we are looking for. And R is, I think it's 5,000, so it's going to be 5 times to the power of 3. So in other words, the I at T is equal to 0 is going to be 1 over 5,000. So this is the I at T equal to 0, and it's going to be in amp. So now we know the magnitude of the I at T equal to 0, so I can go ahead and put initial condition general solution. So if I use, so this is 1, and then we know at this, so now here we go ahead and use initial condition at general solution. This is in general solution. So let's go back and look at this is the general solution. So basically we want to go ahead and put T equal to 0 in that equation. So, so go ahead. So the general solution at T is equal to 0 is going to become the 200. Let me look at what was the equation. So 200 times 10 to the negative 6 cosine 200t plus 200 times 10 to the negative 6 let me put 0 here for the t. So the t is 0 plus 200 times 10 to the negative 6, and this times is going to be 6 sine 200 times t, which is going to be 0, plus the k e to the power of negative 0 divided by tau. So basically in this equation, everywhere we have t, we replace the t with a 0. So it's going to be 0 divided by tau. Now we know that the I at T0 is this one. So this is the I at T0. So if I substitute that, so it's going to be 1 over 5,000 is equal that, and this term, the cosine 0 is going to be 1. So the cosine 0 is going to be 1. So I'm going to have the 200 times 10 to the negative 6. This term is going to be 0 because sine 0 is going to be 0. So it's going to be 0. And this one, the e to the power of 0 is going to be 1. So it's going to have the k value. And here, I think here, so it's negative. So here is going to be negative. So because we have a negative 1 here, so it's going to be negative. So it's going to be, yes, we have the negative 1 over 5,000 is going to be there. And then if you do the calculation here, the k would be comes out as the negative 400 times 10 to the negative 6 amp. So it's going to be the k. So we find the k, and because we find the k eventually, if we go and substitute all the values in the initial in general solution. So if we substitute the k in the general solution, so we have the solution. So basically, try to squeeze it here. So if I go ahead, um, let me draw a line here. So I'm write the rest here. Um, let me. So if I come from here, let's down it here. So therefore, the general solution would be becomes the we know that is going to be the IT is going to become 200 times 10 to the negative 6 cosine 200 t plus 200 times 10 to the negative 6 sine 200 t plus the and for the k we have then it's going to be negative 400 times 10 to the negative 6 e to the power of negative t over, and the tau is the RC. So it's going to be our general solution that we have for this circuit. Now if I go ahead and try to draw this general solution to see how it's going to look like. So let me rewrite the general solution again here. So I'm going to say that the IT is going to be 200 times 10 to the negative 6 cosine 200t plus 200 10 to the negative 6. It's going to be sine 200t and minus 400 times 10 to the negative 6 e to the negative t over RC. RC. So if I go ahead and plot this equation, what I'm gonna get is gonna be something like this. So I'm gonna have two parts, and it's gonna be some. The first part is gonna be look like. Sorry, it's gonna be look like this. So it's gonna be form of sinusoidal form. And then we have I have the second part that's gonna look like something like that. So this for the so also it's gonna be the time, and it's gonna be the I. So the green line that we have, the green line is the result of the source. So this is it's so it's gonna be the response for the source. So it's the result of result of AC source. So what we have in green, so that sinusoidal part that we see here is going to be the results of the source we have. So that sinusoidal part. So because we have the AC part, is the sinusoidal is going to go up and down, go up and down. So we see the I in the system is going to be changed by changing the source. The other one that we see here is as a result of the initial condition, is a result of the initial condition in the system. Initial condition. Do you remember in the system at the beginning that the capacitor was charged to 1 volt, so it was already, the capacitor already have some energy into that. But you see, as soon as we close the key, that initial condition eventually is gonna fade away. It's very quickly, it's gonna fade away. It goes toward 0. So actually, if I want to draw that, I have to draw it much more, goes towards 0. So it goes like that toward 0, and it becomes 0. It's very quickly it becomes 0 and fade away. And that part, which is as a result of the um, initial condition. So if we look at that, this part is going to be this green part. So this is the green part that we have here. So that's this, and then this part is the part that's gonna, it is this one, the part that is gonna fade away very quickly. So this is the this one, and then you can add them together, or in this case subtract them to get the eventual solution for whatever happened in the system. So this one is going to stay in the system as long as the source is connected. This part is going to fade away very quickly.